LC-MS is a powerful tool that combines liquid chromatography with tandem mass spectrometry for maximum sensitivity. The process is simple. First, the LC separates the sample, which is then ionized by ESI. Once inside, the system performs a two-step check, selecting ions in MS1, fragmenting them, and analyzing the results in MS2. This ensures highly accurate identification and quantification for every analysis. Working principle.
The process begins at the nebulizer, where the liquid sample from the LC is converted into a fine spray of droplets. These droplets contain both the mobile phase and the sample molecules. As the solvent evaporates, charged ions are released. These ions are drawn into the sampling capillary, which acts as the entrance to the mass spectrometer's vacuum system. The ions pass through a skimmer and into an octopole ion guide. This stage uses electromagnetic fields to focus the ions into a narrow beam and move them toward the mass analyzer while removing neutral molecules. The ion beam enters the first quadrupole mass filter. Here, the instrument is set to allow only specific parent ions or precursor ions of a particular mass to charge ratio to pass through, while others are discarded. The selected parent ions enter the collision cell. Inside, they collide with a neutral gas, like nitrogen or argon, causing them to break apart into smaller product ions, which is fragment ions. The resulting fragment ions pass through a second quadrupole mass filter. This filter selects specific daughter ions for detection, providing a fingerprint that confirms the identity of the original molecule. The selected ions strike a conversion dynode, which releases electrons. These electrons hit a secondary dynode and enter an electron multiplier, which cascades the signal into a measurable electrical current. The final step is the generation of a mass spectrum. The detector translates the ion abundance into peaks on a graph, where the x-axis represents the mass-to-charge ratio and the y-axis represents relative abundance.
Instruments components. The solvent reservoirs contain the mobile phases, such as water and organic solvents. These solvents are first passed through a degasser, which removes dissolved gases to prevent bubble formation and ensure stable flow. Next, the high-pressure pump delivers the mobile phase at a precise and constant flow rate. The sample is then introduced into the system through the autosampler, which injects a measured volume into the flowing mobile phase. The sample enters the chromatographic column, where compounds are separated based on their chemical properties and retention times. The eluted compounds then enter the ion source, where they are converted into gas phase charged ions using electrospray or atmospheric pressure chemical ionization. These ions pass into the first mass analyzer, Q1, which separates ions by mass to charge ratio and selects the precursor ion. The selected ions then enter the collision cell, Q2, where they collide with an inert gas and fragment into product ions through collision-induced dissociation. The fragment ions are then analyzed by the second mass analyzer, Q3, which filters and detects only the selected product ions, providing high selectivity and sensitivity. Finally, the ions reach the detector, where they are converted into electrical signals. These signals are sent to the data system, which processes the information to generate chromatograms and mass spectra for compound identification and quantification. Recent technological advancements. Real-world and cutting-edge applications. LC-MS is essential for pharmaceutical and clinical analysis. It plays a key role in drug development and bioequivalence studies. It is also widely applied in therapeutic drug monitoring to precisely quantify drugs and metabolites. Whether analyzing biological matrices like plasma or urine, this method maintains high sensitivity and selectivity, even at trace levels. For environmental and food safety, this technique detects pesticides, antibiotics, and emerging contaminants in water, soil, and food samples. Its high selectivity allows for efficient multi-residue analysis within complex environmental matrices, ensuring safety through highly accurate and reliable detection. Strengths, limitations, and future potential. LC-MS offers extreme sensitivity and the ability to detect multiple analytes in complex matrices with excellent precision. However, it does involve high maintenance costs and requires skilled operators to manage complex data processing. Future advancements in AI and automation are expected to make these systems faster and more sustainable, expanding their use in personalized medicine and metabolomics.